Hi, everyone. Thank you for joining us for this in-person and remote IOE MICDE seminar. If I'm not mistaken, this is the first IOE seminar that's in person in the last 2 years. So it's my great pleasure to introduce Professor Scheinberg. Professor Scheinberg is currently a professor and director of graduate studies at the School of Operations Research and Information Engineering at Cornell. Prior to that appointment, she was a professor in the ISC department at Lehigh University, and before that, she was at IBM. Professor Scheinberg's main research areas are related to developing practical algorithms for various problems in continuous optimization, examples of which are machine learning, derivative reoptimization, and convex optimization. Professor Scheinberg has received numerous prestigious awards from the optimization community. She's a recipient of the Lagrange Prize from SIAM and MOS and the Farkas Prize from Informs Optimization Society. So this seminar is very special to me, not only because it's my first in-person seminar in IOE, but also because I have a special connection with the speaker. So Professor Scheinberg was my postdoc supervisor for 2 years, and I want to take this opportunity to thank her for being a great supervisor, mentor, collaborator, co-author, and friend. Thank you, Katya. I can't thank you enough for all your help and support. So today, Professor Scheinberg will talk about adaptive optimization algorithms with stochastic oracles. Katya, it's our great pleasure to have you here. The floor is yours.
Okay, thank you. And I'm so glad to bring you all together. Each other. Yeah, so it's great to be here, and thank you for the invitation. Yeah, I actually wish I kind of had more time. This was probably not a good semester to come because of, have to go back to teach. And I wish my students could hear this introduction. I appreciate it.
It's recorded. We can make it available.
Yes, exactly.
One of your students started.
Okay. Okay. Well, I'm talking about the undergrads. These students are fine. Okay. Right. So I'll try to challenge the statement that I'm trying to work on practical methods today. But really I am trying to work on practical methods. Okay, so what is this whole thing about? So this is really going to be an overview of some work that's been going on for several years, and sort of the way it makes me and my colleagues look at things. And it has actually started not for stochastic optimization, but eventually everybody has to do stochastic optimization, so we do too. And so we are looking at the stochastic optimization problem in its kind of pure sense. So we're trying to minimize some objective function, which is not known to us. And we assume that we can obtain some approximate information about this function. And so we will be talking about what it means. And the approximate information is the function values and the gradients. And at all times when I say gradients, I also mean same thing can apply to Hessian information. I just, keeping things simple here, depending on whether you are trying to use the second order method or not. But so this is the notation. F here is a random estimate of phi, and G is a random estimate of its gradient, and phi is the real function we want to optimize. Okay, so the standard kind of setting where what people use in machine learning and many other applications is the assumption that this F is an unbiased estimator of phi. I should say phi. Albert's teaching me to say phi, which I should know better, being Russian as well. So yeah, okay. So this is an unbiased estimate, and the gradient is also an unbiased estimate of the gradient of phi. And moreover, it's also often assumed, and this is something we'll challenge all of these assumptions in the sense that say, well, maybe we don't want to make them, maybe we don't have to make them, and what happens if we don't? And one other assumption is that the actual, so this is typical machine learning. So you have an unbiased estimate of the function value itself, and you take the gradient of this unbiased estimate, and that is a differentiable function, and that will give you an unbiased gradient estimate. So this is like a nice, simple setting, but it really does not always apply. So this is general setting. This is what is usually assumed, and we're going to go a little bit beyond that.
So is there no assumption on the variance of these random?
No. Variance. I mean, it's all about the variance. So exactly, right. And this is exactly the key point, right? So hold that thought. I'll ask a question to the class in a minute. So, okay, so this is a picture that you may have seen in various forms. It's stochastic gradient. It just randomly wanders, right? But just to be, kind of self-contained in the stock, in principle, the stochastic gradient algorithm estimates the gradient somehow, computes an estimate of the gradient, and then it takes a step in the direction of the gradient with some step size parameter. And so the key here is really what is this parameter, what it should be, how can you select it, and what, as a result, is your convergence, right? So this is basic. Okay, right, so here we go. So if you think of gradient descent versus classical stochastic gradient descent, so the gradient descent, you have G is essentially your gradient or something very close to it. But you can actually relax this assumption a little bit. And then you can take steps that are something like this. So 1 over L is the Lipschitz constant of the gradient of F. So it's a standard of phi. So it's a standard thing. So it's a constant step size, and maybe you can even do better. In fact, this is kind of a lower bound on your step size. And this is going to be key thing in what I'm talking about. So the step size should not get too small because it doesn't have to. And it can actually be larger if you're smart enough to pick it somehow. And that comes from the kind of the gradient descent. And if you have a stochastic gradient descent, then you basically just drive your step size to 0, and that's how you get convergence, but you cannot get convergence with a fixed step size, usually. Right? Okay, so yes, what's the difference between these two pictures? Thank you to John. Variance. Exactly. So the difference is in the variance. So the problem here is that the assumption is that the variance is, well, this is approximate in expectation, but the variance is just something. It's typically assumed to be bounded. Sometimes it's assumed to be bounded in some more clever way, but it's just bounded. And in fact, and this is one of the arguments for my talk today, is that just saying it's bounded makes us misunderstand a lot about convergence of these algorithms. We need to really kind of connect the variance to what happens. And here is an example. Okay. So on the right, let's go to the right. So this is, for example, from the paper. It's a big survey paper by Botu, Curtis, and Nossedal. And the assumption on the variance is that it's bounded by some constants plus some constant times the gradient squared. The reason that this is here is because this means that the gradient, variance is allowed to grow. So it doesn't have to be bounded, but it grows in a certain proportion to the actual gradient. And so if this piece here is not 0, that means, so think about it. If the piece is 0, then if gradient gets smaller, so is the variance. So you're kind of lucky. And it's a very particular situation about which a lot of papers have been recently written. It's called interpolation conditions. Some people argued, well, it's exactly the case. One can argue with that. But if this piece is 0, then you're sort of in a lucky situation. And yet you still, the step size you can take is 1 over L times MV. So the L is the Lipschitz constant, but MV is what sits here. So even if you're lucky, you have this variance sitting there, and it directly affects the size of your steps. And if it affects the size of your steps, it affects the number of iterations. So you can work less and have higher variance, but take more iterations. Or you can try to reduce your variance on every iteration of the gradient, right? And somehow work harder, reduce your variance, and then you'll take larger steps. And there's a trade-off, which in some cases is just 1-to-1. There is no even both things give you the same convergence, but in some cases it may be a different trade-off. Okay, So, and then if this MC is not zero, then you have to drive the gradient, the step size to zero. The convergence rate actually suffers. Now, on the other hand, here is a different set of assumptions we had in several papers that says basically, okay, I'm not going to talk exactly about variance, but it's almost the same thing. I'm going to bound the difference between the gradient and its approximation by something. This something is indeed something that should be going to zero or being small or sufficiently good or whatever you want to call it. So you have to work to get this. But it only needs to hold with some probability. So it does not have to hold. And that probability actually doesn't even have to be extremely close to 1. So just with some fixed probability, sufficiently large, you just want your accurate gradients. And if you don't have them, oh, well, what happens then? Is the question. Okay. Any questions so far? So what we're going to do now is I will first argue about more general setting of making assumptions on the stochastic oracles that we have. And that's dictated by, so I'm going to go kind of backwards. I'm going to talk about the stochastic oracles, which is what I'm interested in kind of generalizing. And then I'll talk about how these oracles came about or how they've been used. Well, I'll give examples, but also how they've been used in theoretical analysis of different algorithms. Okay, so yeah, sorry, before I go there, this is the motivation. Variance matters. So this is a summary of what I just said, basically. If you have larger variance, you have smaller steps. So you're not actually gaining anything, but also because you don't know the variance typically of your data, the step tuning is really hard. While if you are, purposefully work to reducing the variance, the methods become much more robust and much more stable. And you can actually do some kind of classical tricks such as LBFGS and other stuff. So it is, it may pay off to reduce the variance because even if the theoretical convergence rates are the same, you actually can do extra things and the methods become more robust. So this is.
So in the previous slide, like with the probability delta, it can be anything, like you don't care.
Yeah, yeah. So it's an interesting, yeah, exactly. So in most of our analysis, we actually allow it to be anything. So exactly, that's why it's not the same as variance. But right, so it depends on the algorithm. In some cases, we had to assume slightly extra conditions, usually not on the gradient, but function values. So I'll talk about this. Okay, so this is the, yeah, right. So this is to that point. So this is my general suggestion for defining stochastic oracles. And this is arguably may not be the best thing, but, and it takes a while to absorb, but this is what, we're trying to work with right now because it's kind of nice and uniform. So an oracle, first order, second order, 0th order, doesn't matter. It has basically this going to be computed at particular point X, right? And it's implemented for a pair, M and delta. So M is the accuracy, delta is the reliability, it's the probability, right? So for a particular pair, I can produce something that satisfies this condition. So that's my requirement on the oracle. So given a pair M0 delta 0, I should be able to do this. So my oracle spits out something that satisfies this condition. So the function approximation minus the function itself is less than particular accuracy with probability at least 1 minus delta. Same thing for the gradient. Given a pair M1 delta 1, I take I produce a gradient estimate such that the norm is that accurate with this probability. Okay, so this is what I want. Now, the point is that can I actually do it for any pair? So this is what we'll talk about in the very end of the talk. Different algorithms assume that my oracles can be implemented for a variety of pairs. Okay, so for example, if M0 is very large, then it's easy to implement such a oracle. If M0 is tiny, it's harder. In some cases, it may not be possible, and I'll argue that. And in some cases, it is possible, and the different algorithms assume different. So basically, the assumption will be on the set S0 and S1, which is the set of pairs over which the oracle is implementable. Okay, and of course, there's a cost. So now if you define the oracle implementable over a particular set of pairs, for every pair, you can define a cost. And then you can actually analyze your algorithm from the point of view of what kind of oracles you've used along the way with different pairs and different costs. Okay?
Yeah. So I'm a little confused about the oracle. I thought like accessing F, that is what the algorithm can do. So do you need to access F and then come up with something else that satisfies stronger properties?
So this is it's very often that algorithms in themselves include the way to produce these oracles, and you'll see how that actually works. So I'm trying to separate the two things. I'm trying to say I'm going to produce an algorithm that requires these things, and then I can plug in different situations. And so, yes, there will be a procedure within my algorithm that actually computes this F with this particular requirements, but I can do them differently. So I'll give examples of these oracles right now, and you'll see basically how I can. So I'm really just trying to keep them kind of separate. And so this F is not exactly what you would think is like one sample of your machine, like, machine learning loss. It's an average, for example, right? So you decide how much to average. So this is exactly the example I'll talk about right now. So any more questions or objections? More objections. Okay, so this is, all right, standard machine learning. Let's think about that. So you have a loss function. Notice I call it L. So it's computed for a given input X over data point Z pulled from a distribution. And then phi is just the expected loss. And that's what we want to optimize. So the function value estimate and the gradient value estimate are just the mini batch estimates of this. Sorry, the cell is different from the cell, but they should be the same. Okay, so that's like familiar setting, right? There's no question about it. So now we can, taking assumption on the variance, we know how hard we have to work, and we can produce the oracles that we want. So this is the standard assumption on the loss from the paper by Botu, Curtis, and Nosadel. And if we basically, so what do we need to do? We want to produce this kind of oracle. We want to produce a gradient, and function values are similar, but we want to produce a gradient estimate such that in the norm, it's less or equal than M for a given M with probability 1 minus delta. You just use Chebyshev inequality. It's nothing to it. And basically you say, okay, if I keep the sample size of my mini batch sufficiently large, specifically this large, see delta here, M squared here, right? M is small, this is growing larger, of course. So if I use Chebyshev inequality, I get exactly, I know how to implement the oracle. And the cost of the oracle is exactly that mini batch size. Well, it's proportional to that because you have to do some computation for every point in the mini batch.
I have to, why is it a mini batch?
That's what they call it. I don't know. I'm sorry. Exactly. It's not a mini batch in my case, right? Yes. Because batch is the whole data. So in machine learning, the whole data set that you have is the batch.
Really?
I know it's very annoying. The contamination of my optimization lingo is disturbing me. But I'm used to the fact that if I start saying, sample size or whatever, mini batch is easier to understand for some audiences. I'm glad this is not necessarily the case here.
Mixture, be careful.
Yeah. I'm still saying step size. I'm not saying learning rate. And see X here, X. Okay, Okay. All right, so now I'm going to kind of challenge that whole idea because so this expected loss, which is called expected risk for bad reasons, but it's expected loss minimization we just looked at, is minimizes some loss function, and it is assuming that assumes that the loss function, each loss function is differentiable here with respect to x. But usually in machine learning, what you really want to optimize is expected risk, which is the probability of your predictor making a wrong prediction, right? So this is a probability that makes a wrong prediction. So if you actually look at a batch or a mini batch on any finite set of data points, your function, this probability will look like this with respect to x, right? So basically, where does this come from? It's because, you know, you have a think of just linear classification, right? You're changing your linear classifier a little bit. For a while, it does not misclassify any more new points, but then boom, all of a sudden it jumps by one, right? Then it jumps by one. There were years ago when people were saying, well, it's a discrete optimization problem. It's NP hard. Really? But it's not. It's just a noisy approximation of a nice problem. This is my phi. My phi is an expectation. If my distribution is nice and smooth, and the expectation is a perfectly good function. But what we get is this, right? So now all of a sudden we have a good approximation of phi itself. So this is zeroth order oracle is there. It's perfectly fine. It's just, you know, compute the error on your batch or mini batch, right? The number of misclassifications or percentage of misclassification, and it gives you a good approximation of the smooth function. But if you take the gradient, it gives you nothing, completely nothing, right? So what do we do in this case? Well, usually we replace this function with something else, but this also comes up in simulation optimization in some cases where it's much harder to replace functions. And so, for example, what you can do is a very, simple and dumb thing, which is called finite differences, which you all have seen probably in some classes long time ago. Well, for some of you, not so long ago. But, so finite differences, you compute. So if you have function values that are pretty accurate, but the gradient is garbage, you just basically interpolate these function values somehow. So this is forward finite differences, a classical example, and this is central finite differences. It doesn't matter. These are known to be better, more accurate in general, but both of them would work in principle. So what's the idea here? I'm only using function values and I approximate directional derivative for every coordinate in this case, by just taking the difference, like calculus, what to learn in calculus, you take one function value minus another, divided by the step size, and you get what you want. The only thing is that the function values here are not exact. If I put in phi here, I would approximate the gradient very accurately, but I have an error. So the theorem basically would be that if my error for all my sample points that I have here is bounded by something, then this would be my bound on the gradient. So this is my first order oracle that I extracted from having the function values. So this is my first order oracle, and this is the guarantees I have for it. So if this happens with sufficiently high probability, then this happens with the same probability. That's the direct consequence. But you can notice that this estimate is always biased. I can never get it better than this. Now, this sigma here, so the L is the L and the N is the dimension. Sigma is the step, right? So how far I go to. And this is the noise. And you can see that I cannot drive sigma to 0, because if I make sigma 0, this term will explode. So there's a trade-off. And in fact, sigma should be here of the order of 1 square root of epsilon. And here is like square root of epsilon squared. But no matter what I do, this is a biased estimate. So that means in my Oracle, I can only implement it as long as the accuracy I require is bigger than this. I cannot do better than that. Okay. So if I work with such an Oracle, I better be aware of it and include it in the analysis of the algorithm, which we can do. But this is still a valid first order Oracle to some degree, right? Okay. Anything else I should say here? Any questions about this? Okay, cost is an important thing, right? So the cost is annoying, right? You have to compute n+1 function values to get that gradient. This is why people don't use it typically, because dimension can be large. But I will argue that it may actually still, because of the variance, may be the right thing to do. So here is an illustration of basically, so I gave you like a motivation from the expected loss, expected risk, which is this crazy function that is step function. And well, you can make it continuous by turning it into a sigmoid. So the sigmoid is something that kind of approximates the step function, but it's nicely continuously differentiable, even the black version here. So I plotted here sigmoids for A1, A equal 10, A 100, and A is the parameter here. And so as A grows larger, the function becomes more and more crazy. And actually, what happens is this is Lipschitz constant, right? That grows large. Okay, so here's the plot of the sigmoid. And here I decided to approximate it using some kind of, so I took particular X, I took some random samples around X, I computed the sigmoid, and this is, so expectation is what I'm trying to look at, but then I take a sample and I approximate this expectation with the sample. So this is kind of my expectation and this is the sample. Okay, so, I mean, function computed on a sample, right? Approximation of the function. So this is my phi and this is my f. And you can see that they're really quite close. The noise is small, you know, it's a perfectly good one. And this here are actually gradients. The gradient of the sigmoid obviously looks kind of like this, right? It's very small, then it gets larger, then it grows, then it goes down. And so this is the sample gradient computed two ways. One is by taking the actual gradient of the sigmoid function and averaging it out on the 100 samples. And the other one is doing the finite differences. Okay, so it looks all good. Now, not so much. Right, so the red one is still the function approximation, still good, still accurate. What did I do? I changed A. I made A larger, right? And now there are two gradient approximation, and the black one is forward finite difference gradient, and the blue one is just the gradients, the way machine learning does it, right? Take the gradient of the sigmoid itself and average those out. And you can see the variance, right? You can see the variance in the black one. It's not large because it is based on function values that don't have a large variance. So these red guys don't have a large variance, therefore the black guys don't. But the blue ones, they're kind of their own beasts because of large Lipschitz constants, and the variance is very large. So remember, large variance means smaller steps, longer convergence. So maybe even if preservation cost is higher, it may be better to do that than actually use a very noisy gradient. So, I mean, these things may be obvious when I say them, but the whole point is trying to actually put them into the analysis and quantify, right? Exact ways. All right. I'm going to go to the algorithms now so we can take a breath. Oops, sorry. Anything? Any questions? It's a small font, hard to fit in. Okay. So, right. So now it's going to be a 5-minute crash course on adaptive optimization methods. And so I assume most people know line search here. How many people know trust region? Okay, how about cubic regularization? Somewhat fewer. All right, so we're gonna, yeah, exactly. This is one adaptive framework where I claim they all fit to some degree, but not really. It depends on how you argue it. But I'm also talking about the stochastic version. So that's but in general, I mean, this is all we do in unconstrained optimization. There's nothing else we do. We construct a local model at a current iterate of our function phi around current iterate x, and I am talking about constructing this model using stochastic oracles. So this model, I'll tell you on the next slide what this model looks like, but it's basically either linear or quadratic, right? And then using this model, I compute the step. I decide where I want to go. So the step tells me, okay, go here. So the step tells me to go somewhere. Well, this step tells me I should move in a particular direction because this is where the model is improving, right? Somehow the model is improving in some direction. That's where I want to go. But I don't quite trust it. So I'm going to check if this is sufficiently large. So this is the improvement in my actual function. And I'm checking if it's sufficiently large. I should have probably not used phi here because I can't check phi. I don't have the access to it. So I'm guessing in some sense, not exactly checking. So I'm checking, but using an exact information. But this is generally the framework. So compute the step, check if I get an improvement, and then two things can happen. I either have an improvement or I don't have an improvement. The belief is, that comes from deterministic optimization. If I don't have an improvement, it is because I went too far. Why? Because you always believe your model. You think your model is great. So I went too far, I have to cut back somehow. I have to, and if my model comes from, say, Taylor series expansion, eventually, if I'm close enough, I will always get an improvement. So that's how the deterministic optimization works and all the analysis. So now I am in a different situation, but I'm still going to be blind to the fact that I may get a very crappy model. And I'm going to just go and assume that if I didn't get an improvement, I went too far. But I also will say, well, okay, maybe I should also recompute my model. And this is actually where it comes. We were talking with Michelle today about how to recompute the model. We just recomputed, but maybe there's a smarter way to do this. Okay, so these are particulars. So I told you it's going to be a very quick crash course. So line search, you basically, the model, I mean, you think of line searches or gradient descent as basically just, you take a negative direction of the gradient, but if you're using the Newton method, then you would have a Hessian here. But in general, you just have to have some positive definite matrix. It can be identity. And in which case you basically can view your line search with alpha k as a step size parameter as minimization of this model. So it's a strongly convex function with parameter dictated by alpha k. So if alpha k is smaller, then your step size is smaller, basically. So this is the step size. Okay, and again, H can be just identity, it doesn't matter. And then you check the sufficient decrease condition by using the F approximations, and this is like standard Armijo rule, but you can do other things. So that's the line search. Trust region is different because what you do with the trust region is you again construct a quadratic model. By the way, just wanted to say that it's phi here, which we don't have, but it doesn't matter because when you're minimizing a function, the constant is irrelevant. So we just for completeness, we write phi. But in general, it's a quadratic model, but now it doesn't have to be positive definite, the H, so you don't have to have convex model. And so you minimize this not necessarily convex quadratic within a ball of radius alpha k. So here alpha k dictates the radius of the ball in which you do the step. So it's actually limits the exact length of your step. Here, this is more like a parameter that affects the length of your step, but it gets multiplied by this, right? So there's a little bit of difference. There's another sufficient condition for reduction, which is standard for trust region. I'm not going to talk about this at all. It just, if you're familiar with I just want to point out that all these methods do these three things: compute the model, reduce the model, and check the sufficient decrease. Compute the model, reduce the model, check sufficient decrease. And finally, cubically regularized Newton is basically, you get the approximation, which is second order, using some efficient approximation, and then you add this term, that's by cubic regularization. And it is good for nothing method, except for it has the optimal convergence rate compared to these two. So its convergence rate is better and it's optimal for non-convex optimization. But otherwise, it's really not necessarily the most practical. Yeah.
For the Hessian in cubically regularized Newton's method, do you also consider stochasticity over there, or is
Yes.
it only on gradient?
Yes, you consider stochasticity on that as well, right? So I didn't put the second order oracle, but yeah. So far analysis for this, I mean, I'll give the summary of all the results. The analysis we've done for this is only under some restricted conditions, so stochastic Hessian, stochastic gradient, but deterministic function values. I mean, now we know even better how to extend this, but it's just a hassle, and you know, it's not necessarily. I mean, it's not a very useful method in practice, but it's it could be done. Okay, so this is just to get an idea. Like now, I'm gonna just give you a very, very quick overview of like how you can even analyze these methods under these conditions. So what happens? I mean, remember stochastic oracles. They say they should be accurate enough with some probability, but they may fail. And as Nikhil was asking, what happens? They can be total garbage. And in principle, yes. So there are basically 4 situations that can happen. So this is my function. This red one is my model. Again, I'm drawing a linear model just for simplicity. And these purple things are my function values. Okay. So I was thinking about this yesterday, and I was like, can I make an analog about this? Like, say you want to go on a date, somebody sets you up on a date and they say, this is really good date for you, right? And then you go and ask some other people, because you have some people who know that person. Is it, do you really think so? These are the function estimates, right? These are your friends, that's supposed to be your friends. And they should tell you whether you should take that step or not take that step. Okay. So this is a good situation where somebody set you up on a really good date because they really, you know, the model is good. And your friends are saying, yeah, it's going to be a good thing. You're going to improve your situation. So you go and take the step and you're happy. This is a situation where somebody sets you up on a really bad date. Yeah.
Just to clarify, so the curve, is that the real function? Okay, and the points are the stochastic aspects. Okay.
Exactly. Yeah, the truth, the purple curve is the truth.
Mhm.
Right, and these the red one is the model, and these are these Fs. Right, so here somebody is setting you up on a really bad date, but your friends are saving you, saying no, this is not going to lead to any improvement, so don't take that step. So you don't take that step. What did you lose? Well, not much, but you lost an iteration, right, for your algorithm. So you made an iteration which is not worth it. Moreover, you're going to decrease your step size because you think you went. I mean, the only reason you think you can fail is because you were making a very large step, so you'll decrease it. I don't have a very good analogy for data analysis. You went too far. I don't know, but okay. Then another situation that can happen is that actually the direction was very good. You should have taken that step, but your friends lied to you. And so you don't take that step for no good reason. So again, you wasted the step. Again, you decrease the step size, but you at least didn't move. This is a situation actually, which is kind of quite problematic for analysis. And this is where we often need to struggle, is that if you have both bad direction and bad advice, then we're taking steps that are increasing the function value instead of decreasing it. So we're really damaging whatever good we have done. And that is difficult for analysis, because when you're trying to analyze convergence rate, you need to basically count how much improvement you get and say that, okay, you cannot improve infinitely. So this is your the number of steps that you need. But these things can be damaging. So
You mentioned in a sort of offhanded way that you might recompute your model, right? So is that a situation where you can learn a life lesson and recompute your model?
yes,
somehow?
yes,
Okay.
exactly, right. No, that's right. So basically, okay, so this is the key thing. So true iteration is this. These are all bad, false in some sense. Well, these are all false iterations. So the true iteration is the one where everybody's doing their job. And if everybody's doing their job, there's a probability to that, according to our oracles. So now you basically just need to say, okay, well, how big should this probability be of everybody doing their job? So whenever things go bad, it does not damage me too much. So on some iterations, I'm going to make improvements. On some iterations, I'm going to fail. On some iterations, I'm going to make even worse, right? Like the damage my improvement. But overall, if the probability of good steps is sufficiently large, then overall, I will have convergence, either with high probability or an expectation, depending how you do analysis.
But it's not just probability, right? It's also the magnitude.
So,
Right, so there's a balance between these.
so okay, right. So this is the key thing is like how much you can, right. So the damage, right. So the magnitude of, that's exactly right. So the magnitude of this is kind of known. It's basically related to the size of your gradient, right? Exactly. So the magnitude of the damage, like here, you don't have any damage. You just reduce your step size, right? But here you can have damage. So, right. So the damage is actually related exactly on how bad these estimates can be, and you have to connect the two. That's exactly right. So for example, if these estimates are accurate only with some accuracy, and this is one of the papers we have with Albert, so it cannot get better than some epsilon f, then once the gradient becomes too small, bets are off. You don't converge anymore. But that's natural, right? If your function is not known exactly and you cannot possibly get it more accurately, you will eventually stop. But there's exact connection of where you converge. So you know until what time it works. Oops. All right. Okay, we basically have two heavy slides. This one is less heavy. The next one is heavy. The next one is summary of results. This is the idea that I kind of already said, like how you can make all these things account for. So basically, this is the high level idea. So there's a key term here, this alpha k, right? I showed you that in every adaptive algorithm it exists and it adapts, it's adjusted, it increases, it's increased or decreased. So I can visualize the log of it as a random walk, basically. It's random walk because it decreases because my model is bad and it happens with some probability. So it is a random walk. So in deterministic optimization, we remember this alpha equals to 1 over L thing. So we know that if alpha is small enough, we will always have a good step. So that's why we say we don't have to worry about alpha getting small. It will at least be 1 over L. So it's a similar situation here, except for accidentally, we can make alpha small because we're making these bad steps. Just we accidentally make wrong choices, bad models, and we always decrease the step size, so it can actually go below. So think of this level as 1 over L, and we can be above it, or we can be below it. So the key property of all these methods, and this is how the probability of good iteration should work, is that once we're below this level, we should be more likely going up than going down. It's very simple. So it's a random walk that tends to go up, and you can very much, you can very, well, not very easily, but you can estimate how frequently it returns to basically this level. And then you can count the number of iterations. So when you're at this level and you take this step, this step is a successful step because you increase your alpha, you've taken a successful step. So if that iteration is true one, you've made a major decrease in your function value. So you have to account for all these different iterations, the large ones, the small ones, the good ones, the bad ones, but altogether you have this, basically count of iterations. And because of your probability of successful step, or, your oracles give you sufficient probability, you can analyze this whole thing and you get the total convergence complexity bound. So total complexity bound, the total number of iterations it will take to get to whatever accuracy you want. And so here is now comes the summary. Okay, so this is going to be a little bit hard to parse, and damn it, I was making corrections just right before, and it's supposed to be 1 here. 1. Okay. All right, so it started with us doing several papers analyzing the case when the gradients were random, the Hessians were random, but the function values were exact. And I represent this by the fact that 0, so this pair, remember this is M and this is delta. Oh, okay, so this should be 0 if I'm using delta, sorry, not 1. So if this is 0 and 0, that means that I can compute exact first order, 0th order information, so exact function values with probability 1. Okay, so this is deterministic, basically. So you have deterministic oracle for the 0th order, but you have stochastic oracles for the 1st and 2nd order. And in this case, there are 2 papers as well, 3 papers actually in some sense, but there's analysis for line search. And we show that the complexity of, yeah, I didn't correct. This 2 has nothing to do here, but it doesn't matter. Log of 1 epsilon squares is the same. It's just copy and paste problem. But it's log of 1 epsilon square in the convex case, a strongly convex case, this in the convex case, and this in the non-convex case. I don't give the details what this epsilon is, whatever, if you're familiar with it. The key thing is it's basically the same as deterministic methods. So it's the same complexity. So we recover complexity of deterministic methods. There's a constant sitting there always that depends on the probability of success. And as the probability of success gets smaller, that constant goes up.
Katya, when you introduced line search, you said you put some positive definite HK. It doesn't have to be the Hessian. It can be blah, blah, blah. So for these results, do they require some specific update rule for the H, or?
No. This is just line search with any direction that. Yeah. So I mean, it probably needs. I don't remember exactly. So we just want to make sure that with high probability, the direction we're taking has a positive angle with the gradient, right? So, normally if you have H positive definite and you have the gradient, the H inverse, whatever, it has a positive angle. So we just, yeah.
So as a follow-up question, these guarantees apply for first order solution, right?
So these are first order methods, exactly. This is first order. I think we had a second order. I'm going to show in a second. I think for trust region, we also had a second order. We did. I just didn't put it here. And this is right. So this is a convergence for the gradient for cubically regularized Newton, which is a second order method. Right. So there is, I mean, in some sense, there's nothing exactly fishy. The methods are the way they are in deterministic optimization, except for they compute these random things from oracles, and they impose conditions on these oracles, right? That they need to converge. So this is, that's why I decided not to. I mean, I can spend a lot of time on each method and explaining what the details are, but it's a little tedious. So then we worked on purely stochastic setting, meaning that both the function values and the gradients and the Hessians are stochastic. But essentially, these oracles can be accessed or can be implemented maybe at cost with arbitrarily good accuracy. So we want convergence to the optimal solution. For that, we need these oracles to eventually achieve any accuracy we require. We try to be careful. So the idea is not to, so these are adaptive methods. So the accuracy we require from oracles adapts as we progress. So at first we don't need high accuracy, and then eventually we need higher accuracy. But the key thing is that eventually we may need arbitrarily high accuracy. So we assume it is available for first and second and zeroth order. Right, but this accuracy is only available with some probability, which is fixed. The probability doesn't have to go to 1. It's a fixed probability as long as basically the product of these probabilities is something like bigger than half. This is rough. There are extra requirements there. Then again, we require expected iteration complexity to be, whatever the deterministic counterpart is. So these are expected iteration. This is also expected complexity. This one has actually high probability analysis in it. So we've kind of taken, well, not exactly ideas from there, but the inspiration from here, and recently started looking at line search and trust region under much more relaxed conditions. So there's a lot of, complicated things here, but the idea is that we now say that, okay, our first order oracle cannot achieve, or zeroth order oracle cannot achieve arbitrarily good accuracy, and second order oracle as well. So there's a limit to how good they can be. They're biased and they cannot be better than a particular value. Okay, but then so for any accuracy above this epsilon g, we are able to compute a first order oracle that is, as accurate as we want, up to this accuracy, right? With sufficiently high probability. And again, probability just should be something. A similar thing for the Hessian, which I didn't write down. There is a trick to so this is kind of the bottom line. When you're doing this line search, it is really important to remember the dating advice and the friends. The friends have to be reliable, right? They should not screw up too often, precisely because we were saying that this can do the damage, right? You have to control it. So the assumptions that we have now, and this is here, there are also assumptions that you can make bad decisions, and the analysis was kind of a lot more complicated. This analysis is stronger and better, but the assumption on the oracle is that you can have an error, epsilon f, and you cannot do better than that. But you can also do worse, but with basically exponentially decaying probability. So it's sub-exponential variable. So in simple terms, it's like your friends can lie to you a little bit, and they can lie to you a lot, but it's unlikely. Okay. And so in that case, it's we have analysis already. This paper is already out, and this paper, well, we're hoping to wrap it up really, really soon. So this is for trust region, and this is first and second order, and line search. And the important thing is that once you actually have these biased estimates, basically the oracles are not exactly accurate, you have to be a little careful, and you have to modify the acceptance criterion of the step in both line search and the trust region. So you have to be a little bit more flexible about it. And that causes some trouble with analysis, but eventually, it kind of all comes together. And okay, well, I will not bother with conclusions. It's basically, I said things many times, and these are some of the papers that I mentioned, and I really thank you for your attention.
Time for questions.
Considering the first order methods, I'm not talking about the second order. Sometimes, especially in machine learning, we like to have noise because strict saddles, we want to skip those.
Right.
So in some cases, we would like to have variance.
Yeah.
And the reason is, in that case, you can actually converge to second order solution using the first order method.
Mhm.
So in that context, how is your result? Like, in one hand, we want to reduce.
Yeah.
variance.
Right.
Sometimes we don't.
Yeah,
Now,
right. Yeah, so I haven't looked into this. The key thing here is that when we have this noise, right, it dictates exactly when your algorithms stop progressing. So in our case, it's like, okay, we have this noise and we can guarantee that we'll converge until basically your gradient is small and then you'll get stuck, possibly. And right, so what you're saying is that there is analysis of certain methods where not only you don't get stuck, you actually go away from bad situations. I don't know if they're combinable, but yeah, perhaps, because it depends on the size, right, of the neighborhood, where, like, how close you get to settle point, at which point we'll say, oh, we're stuck, and this other method say, no, you're actually gonna go. So maybe we can even combine the two. Yeah, I don't know.
in fact, that bad situation where you take the wrong step would actually
Yes,
a good scenario. for you.
Right.
It only takes one step, one
Yeah,
wrong
yeah.
decision.
Right,
for
that's
us
true.
to see.
yes,
But yeah.
right, yeah.
So when I first learned about line search method a long time ago, from maybe more practical point of view, people were talking about inexact line searches and enforcing our Mio conditions or Wolf conditions. And so what's the view on that kind of from the lens of this perspective?
Right. Yeah. So actually, it's funny. When I was on sabbatical at Google, I wanted to implement line search, and people said, no, they already implemented. Here's, of course, at Google, it's always their own papers that they read, right? So they there's a paper where they tried exact line search. Now, exact line search, I mean, I don't think it's a practical method, except for very special circumstances, and clearly stochastic optimization is not one of them. But so yeah, so this kind of traditional line search ideas are, they wouldn't work, I think. So what we are, as I was saying, Jorge is forcing me to change the name, like to some kind of multi-directional backtracking. So the idea is that the line search really here means that you're choosing your step size parameter adaptively, and you are using what you had on the previous iteration to kind of suggest what you have on the next one. Now, it's a bit more tricky because if you're actually using Newton method or quasi-Newton method, you do want to try step size 1 at all times first, and then you shrink it, right? So this is still the same, except for now the question is, if I tried step size 1 and I failed, should I just shrink it or should I actually recompute my direction? And so this is, it's not clear. I mean, we're assuming you recompute because it's easier to analyze this way, but we can step back 10 times and then recompute. It still would be fine. It's just analysis will be messy.
I think we have to leave because, yeah, so thank you.